Work energy theorem states that the work done by all forces acting on a body, work done by all forces acting on a body equals its change in kinetic energy. Change in kinetic energy means it is kinetic energy at final state minus kinetic energy at the initial state. So kinetic energy is defined, so it's denoted by Ke. So it's defined like this: half mv square. M is mass of the body and v is speed. So we have to prove this work energy theorem. It means this, if a body, suppose this one state 2, state 1 to state 2, say a body being taken from state 1 to state 2, then the work done by all forces equal to, say, Ke2 is kinetic energy at state 2 and Ke1 is kinetic energy at state 1, right? We have to prove that from 1 to 2, say W is work done by all forces acting on the body is equal to this Ke at state 2 minus kinetic energy, or Ke at state 1. Now we will prove this theorem. So the first case will be when a constant force is acting on a body moving in a straight line. That is, this is state 1 and the body moves in a straight line from state 1 to state 2. Say at state 1 velocity is v1 and state 2 velocity is v2, and say about the force acting on the body, F. So if so this is v1 is speed at state 1 and v2 is speed at state 2, or velocity rather, it should be velocity. And if a is the acceleration, then obviously F equal to ma. So if the displacement happens to be s, so therefore work done by all forces, this F is a vector sum of all forces, so F multiplied by s is ma multiplied by s. So A is so this v2 square equal to v1 square plus 2s. So therefore A can be replaced by v2 square minus v1 square by 2. Therefore work done by all forces, F into s, is half mv2 square minus half mv1 square. So half mv2 square is Ke at state 2 minus half mv1 square Ke at state 1. So in this case we will consider a variable force acting on a body moving along a straight line. So at state 1, as you see, speed or velocity of the body is v1, and at state 2 velocity of the body is v2, and the force acting is F. F changes actually. If acts along the straight line, one dimensional force, but it changes. So in a small displacement ds, what is the work done? F ds. So the total work done is integration of F ds from state 1 to state 2. So that is integration of F. So F we can write as m dv dt times ds. So now see, ds by dt is v, right? In physics you can quickly slip this dt to the space beneath ds. So this m dv multiplied by ds by dt. Okay, so ds dt is actually v. So write this v here, mv dv from state 1 to state 2. Here it is in terms of v. So v1 to v2 speeds at state 1 and state 2. So this work done is m integral is half v square, then putting the integral limits, half mv2 square minus half mv1 square. So that is kinetic energy at 2 minus kinetic energy at 1. So this is the most general case. Here the force is variable force and the particle is moving from position 1 to position 2, or say state 1 to state 2 along the path shown. At the force acting F, and for that work done from state 1 to state 2 or position 1 to position 2, work done is integration of F dot dr from say state 1 here, lower limit state 1 and upper limit state 2. So that means W is equal to integration of here m dv dt dot dr. Now here again I can slip this dt to below dr. So this is dr by dt. So this dr by dt is v, as you know. So work done is equal to integration of m into v dot dv from state 1 to state 2. So we can express kinetic energy as say k for kinetic energy, or ke, whatever energy, that is equal to k. You can express like this: half mv square can be expressed as half m v dot v, because v dot v is v square, as you know. Now you find out a small change in kinetic energy, d of k is, you know, you can apply like this: v dot dv plus dv dot v. We can apply the product rule for this case of dot product also. I mean product of two functions, you know, product of two functions, what you do? Say dd x of say uv is equal to u dv dx plus v du dx. Without this dx also it works. So you can remove this dx, right? So this is the same thing we have done. This. So however, dv is equal to this. So m into v dot dv. So dk k for kinetic energy is mv dot dv. So in our previous page, what we have seen, that work done by all forces from state 1 to state 2 is integral m v dot dv from state 1 to state 2. So this we can replace as we see in this expression. So we can replace m v dot dv by dk. Now from state 1, that is k1, kinetic energy k1 to k2. So this you can write as k2 minus k1, putting the integration limits, or w is k2 minus k1 or ke2 minus ke1. So this proves work energy theorem for the most general case, variable force and particle moving in three-dimensional space.